Hi all. So in today's video, we're going to talk about the Poisson distribution. So the Poisson distribution, this is actually something that we looked at way back in the day, right? Like week 3. It feels like forever ago, eh? But basically, we're going to look at the Poisson distribution by itself now without having to worry about the binomial distribution. So if you kind of remember when we did the binomial distribution, we said, okay, well, we take some trial, we repeat it n times, and what's the probability that this thing happens exactly x number of times? And we kind of had two different ways to approximate this, right? We had the normal distribution for when p and n are kind of close-ish to one another. And then we have the Poisson distribution when they're not close to one another. In other words, if p is sufficiently small. And we kind of remember that the Poisson distribution we had, or this was given to us by this formula, right? This is the formula that we had for approximating the binomial distribution using the Poisson distribution. Now the thing is, we're going to look at this and notice that we don't actually have to have this. We can just, like here we had the mu, it was just the expected value for the binomial distribution. So this was all binomial. Now, if we take away the binomial distribution, just pretend it's no longer there, we actually end up getting what's called the Poisson distribution with parameter mu. So if we're given some parameter mu, then we can just define the Poisson distribution to be this formula. The probability that x is equal to k is given by this formula. Now notice how this k has to be an integer. I guess positive integer. So I'll just do a little plus to say positive. Or I guess we're allowed zeros, so I'll do this instead. Greater than or equal to 0. And this is what's making it discrete, because we're allowing things to be nicely. Now I'm not going to have you solve what the expected value and the standard deviation is. Instead, I'm just going to give them to you. The expected value is mu, which is basically exactly what we expect, right? Since this is similar to the binomial distribution, we expect this to just be mu. Now, the thing that's kind of a little less or a little more weird is that the standard deviation is just square root of mu. So it's a little bit weird, but that's basically it. So let's actually look at an example of this, and then we'll go into a more in-depth example in the next section, or in the next video. So one thing that is known to be a Poisson distribution, and normally with Poisson distribution, I'll let you know it's a Poisson distribution to help differentiate from the binomial distribution. But some things like this example, you should kind of know, okay, this is a Poisson distribution. So basically, it's known that the number of raindrops that fall on a particular square inch of roof in a 1 second interval of time is given by the Poisson distribution. So what do we have here? I have some roof. I have a square inch. So I have 1 inch, 1 inch. And we're seeing the number of raindrops in a 1 second interval. So x is number of raindrops per second. And so we're assuming x has a Poisson distribution with parameter 2. So we're assuming mu is equal to 2. We're just given that. So this tells me mu is equal to 2. What is the variation for the number of raindrops that fall on the particular thing? So variation, remember, is we're looking at the variation, right? The e of x squared minus e of x squared. But in this case, we actually don't have a lot of work to do. So the variation of x, well, this is just the standard deviation of x squared, right? Standard deviation of x, we're already told, is just square root of mu. Square root of mu squared. So it's just mu. And mu, we're told, is just 2. Done. Bam! Look at this! Easy problems. And the big thing here is to kind of notice that this Poisson distribution changes based off the mu, right? It's this mu that changes what this distribution looks like. So here, for example, if I have mu is equal to 0.1, this is my values of k. So remember, these are the points that we really care about. K is equal to 1, k is equal to 2, and k is equal to 0. So in reality here, and this is the probability. So this is P of x equal to, I guess, k here. And so these other parts, it's a continuous graph, but we only care about these particular points. So notice how k is equal to 0 is the highest likelihood in this example. Here, again, if I have a different parameter, here mu is equal to 1, again, we're going to notice 0 now has about a 30, 0 is about 0.36-ish. It's hard to tell. 1 is, I guess, a little less than that. Is about 0.35. 2 is about here. 3 is about here. 4 is about here. These are the parts that we care about for this distribution. If mu is equal to 10, notice how this is looking much more like the binomial distribution. And that's why this is hard to tell from the binomial distribution. Especially if you look at this it looks like it's tilted a little. So this is why it's kind of harder to tell. So notice how these are the points that I really care about, right? 15, 20, here's 11, 12, 13, 14. Anyway, we'll kind of stop here. But what I'll do is, actually, before we kind of go, I'm going to switch to an application to kind of see what this looks like when I go over mu. So here I have an application, GeoGebra, if you don't know it. I've plugged in my formula. I don't know if I can zoom in. No, I can't. But the formula I have, if you can see in the left-hand side, is I have e to the minus m. M is our mu. M to the x over x factorial, which is our Poisson distribution. And as I change my m, you'll see that my formula, here I can zoom in a little, my formula is basically changing. And you can kind of see, it's a little hard to see, but you can see in the graph what happens. So as I increase my mu, you can see the graph kind of change to a more Poisson-y or binomially distribution. So this is kind of what happens. And remember here, the key point is that we're only ever looking at k is equal to 1, k is equal to 2, k is equal to 3, because this is a discrete distribution. So I know that image wasn't perfect. I would say go through and try it with yourself. Try it yourself to see kind of how things work. But yeah, so the thing is that since the Poisson distribution is similar to the binomial distribution, we can actually just keep using our normal approximation for the Poisson distribution. So an approximation for this is just given by our phi's from before. And in this case, the thing to kind of remember is I want mu here and I want my standard deviation on the bottom. And the standard deviation for us is this, square root of mu. So this kind of changes the formula, but not by too much. But it's the exact same idea here. And we can do a very similar thing with the skew normal. So if I want x less than or equal to b, well, in this case, I can just look at phi of z. And then here z, remember, is equal to b plus 1/2 minus mu over square root of mu. And then we can just do 1 over 6 divided by the standard deviation, which is mu, times z squared minus 1. So notice how this is basically the same formula as before, phi of z. And that's it. Now another cool thing, and this is kind of the last thing we'll say before looking at an example, is that they're relatively easy to sum up. So in other words, if I have n independent Poisson variables, so I have x1, x2, x3, etc. up to n, each with parameters m1 through mu n, etc. Then the sum is this Poisson random variable with parameter the sum of the parameters. So this whole kind of thing, I guess I don't want this whole thing actually. I want most of it. So this is like the key point here. I'm going to make this bigger. So it's like a fairly nice thing and something nice to work with for future things. So we'll look at an example of this particular property in the next video with an example. So I will see you then.